we're going to have some short talks on 5G related software and hardware. And the first speaker for this short talk session is Anupa Kelkar. Anupa is product manager for NVIDIA 5G Aerial. And Anupa will give us a presentation on the NVIDIA contributions regarding the Aerial platform.
Yeah, and just as a reminder, each presentation should be around 10 minutes so that we can have some Q&A after the presentation.
Okay, sounds good. Thanks for the introduction, Michelle and Leonardo. Good to be part of this forum. So I'm planning on sharing just a few slides, but even before I share any specific slideware and material, I want to just set the context. What Aerial is really enabling is a signal processing pipeline using NVIDIA's GPU platforms, our OS, CUDA OS, which is architected in a way that it's able to support any underlying GPU architecture. What we have is a common OS, a common platform that can also add drop-in accelerators from our entire CUDA OS, CUDA drivers, toolkits, and libraries, which is fairly powerful to be able to offer drop-in accelerators. And with Aerial, what we have done from an innovation perspective is we have demonstrated both from an industry perspective, where we are bringing in and launching to the market a GPU-based 5G G-Node B with a commercial ISV, commercial partner. In parallel, as we look towards 6G, we definitely recognize and understand that some of the KPIs, some of the capabilities that are being discussed right now in the standards will require a deep integration with machine learning and artificial intelligence. And we hope to be part of the ecosystem that really leads the way towards 6G. So that's our long-term vision. And just to provide a little bit more color and context, I'll share a few slides to talk us through that, and I'll keep it to 10 minutes. Let me know once you're able to see my screen share.
Yeah, I can see the slides. Maybe if you could go in presentation mode so you can see them full screen. Thanks. Yeah, perfect, great, thanks.
Okay. So again, at a very high level, common platform, we are leveraging everything from an NVIDIA OS, drivers, and toolkit perspective. What we have built from an innovation standpoint is really the L1 PHY pipeline, the complete PHY pipeline, ORAN 7.2 split. It's 3GPP release 15 compliant right now in a 44-hour MIMO configuration, 4 layers downlink, 2 layers uplink. And we've been able to leverage the GPU architecture from the grounds up, a lot of the complex floating point math functions for which we've been able to leverage the CUDA OS, various libraries. We have another innovation using NVIDIA's Mellanox Smart NIC for onboarding signal processing packets, if you will, directly onto the GPU memory. We call that idea GPU Direct RDMA. We bypass the CPU mem copy, any latencies associated with the traditional NIC to CPU communication by directly facilitating and onboarding onto the GPU. We have a blue field converged accelerator roadmap. The idea with that is we are evolving towards a data center on a chip. For Aerial being a software-defined workload, we will definitely be able to leverage the same. From the get-go, we are also cloud native. Again, this is the same for all NVIDIA application frameworks. We have all the necessary primitives from a Docker containers and Kubernetes manifests and Helm charts, as well as some additional primitives for the GPU operator to help be operated and execute the workload in a cloud native fashion. So here's some, this is nothing new to most of this group, so I won't spend too much time here. But really, this is what I mean when I say you can drop in acceleration for your applications. These libraries are available. You can find them online through the developer pages from NVIDIA. And this is just a sample of different areas and the specific libraries and APIs that are supported. Clearly, there is a lot more that is available overall from an NVIDIA standpoint. Now, specifically on the Aerial workload as a cloud native workload, here's what we've done. We've been able to leverage GPU, a CPU, and a NIC. Fundamentally, those are our hardware building blocks. There is no proprietary ASIC, FPGA, or any other proprietary hardware involved at all. It's just off the shelf, the same GPUs and NICs and CPUs that are in hyperscalers or in other deployments. We've been able to leverage those. Above that, using the CUDA OS and CUDA toolkit, we have two Aerial libraries today. The cuBB, which is our PHY baseband processing library, if you will, that handles the functions that I have described on the left, but which are you're all very familiar with from an L1 standpoint. And the cuVNF is our library for a fast path towards a GPU IO, if you will. The cuVNF, using NVIDIA Mellanox SmartNIC, we've been able to augment the firmware to also support precision timing, eCPRI front haul onboarding, header data split, if you will. So we've been able to augment the NIC with certain capabilities that are necessary for 5G. We have a rich L2 plus ISV ecosystem. We are also both commercial as well as from an open source engagement standpoint. We've been, OAI was the previous presenter. So also happy to share that we are making plans with OAI to bring them on board as a platform. So this is just a different way of presenting the same information, but it's a 7.2 split cuPHY pipeline. Everything in green is NVIDIA source, and we rely on partnerships and the ecosystem for everything that is in blue or gray. So from an architectural view standpoint, we're keeping it extremely simple. What we have is an L1 and L2 controller that translates the SCF FAPI interfaces into the cuPHY driver, which orchestrates the work on the GPU. The cuPHY actually has the APIs and the CUDA code that execute the PHY pipeline. On the front haul library, if you will, or the cuVNF is basically where we have our eCPRI onboarding or the ORAN compliance to be able to handle the front haul communications as well as the timing. The topology that we currently have established in our lab is along these lines. What we have is we have a switch that really helps ground or as a conduit to the ORU on the right. In this case, it is a Fujitsu ORU that we have first interoperated with. We are also working towards a Foxconn ORU integration. The bottom right, this is our Aerial SDK. We have the Hi-Fi in the SDK, and we have integrated ecosystem MAC and above layers on the CPU. This is all a COTS server. Today, the configuration, the two configurations from a server perspective that we support are, one is a gigabyte server, another is a Supermicro, is where we've also done some integration, as well as Dell. So you're able to plug in the GPU and the NIC cards into COTS existing servers. You can host 5G core node network elements on another server of your choice. And then, the same really setup can be used or extended or expanded to bring in AI applications, bring in AI frameworks, machine learning for various things. One, as a co-located MEC application. Second, as a way to, in a non-real-time RIC configuration. Or again, this is the most flexible configuration that we are using in our lab today, and there's a lot of different possibilities that this configuration could be used for. Now, as we look ahead, one key thing that we are targeting is we want to ensure that a GPU with the common CUDA OS, all of the libraries that are ideal to be drop-in accelerators, are leveraged optimally as you look towards 6G. 6G brings with it so many different asks from a standards perspective. It's going to require and absolutely need machine learning and AI. It'll need machine learning from a learning, from a training standpoint, federated learning, network optimization. It'll need really an AI ML-based air interface in a lot of ways. The spatial complexity will only grow as you look at 6G. On the right, there's some KPIs that we are looking at as you look towards 6G from a standards perspective. So one key thing that I wanted to again summarize with is we are developing a platform. We are developing a platform not only to take to market from a 5G perspective. We will ensure that it's qualified for 5G markets, but we are thinking 10 years out. We have a vision to ensure that GPUs are the platform to help pave the way towards 6G. So I'll pause right here for any questions, please.
Thank you very much, Anupa. And I see we have a question in the chat. And the question is, are there any plans to do similar things on UEs?
That's a good question. And we are definitely thinking about something similar. Again, as a platform, we make our source code through a fairly open framework from a licensing standpoint for research available to anyone who's interested. So there is a way or path towards looking at both the transmit and the receive ends. And yes, on the UE as well. There are definitely benefits of leveraging GPUs. As you know, compute is now becoming fairly distributed. So GPUs on UEs, definitely use of GPUs on UEs, it's something that we are considering.
Thank you very much. And there is another question, and is, could you please elaborate more about the plans regarding digital twins?
Yeah, absolutely. So let me just step back and make sure that the community is aware of NVIDIA Omniverse. So this is NVIDIA's application framework or application SDK for digital twins. In industrial settings today, it is being leveraged. It is also being leveraged internally by multiple other application frameworks within NVIDIA. For example, the robotics team today leverages the digital twin or Omniverse, and they've clearly built customization on top of that for the robotics space to make it a training room for robots to become AGVs. They have also leveraged the same digital twin to then bring in reinforced learning from the real world back into the digital twin. The same, and the reason I was using it, this specific example, was this is a concrete example where there is already significant industry traction on the robotics platform using digital twins. So we want to extend and reuse that same framework. It's a mature framework considering multiple other NVIDIA SDKs also leverage it. We plan to use the same for 5G and first integrate Aerial with Omniverse. And as we develop these blueprints and recipes, plan to share with the ecosystem.
Right. Thank you very much, Anupa, for being here today. I think for the interest of time, we're moving to the next speaker, but I see there are a couple more questions in the chat. So if you could just reply in the chat to those questions.
Sounds good. Yep.
All right. Thank you so much.
Yep.
So our next speaker is Melike Erol-Kantarci. And Malika is a Canada Research Chair in AI-enabled next generation wireless networks and an associate professor at the School of Electrical and Computer Engineering, Computer Science, sorry, Electrical Engineering, Computer Science at University of Ottawa. And Malika will talk about ML and ORAN related work from the NETCORE Lab at University of Ottawa.
Thank you very much, Leonardo, for this nice introduction. And thank you, Michele, Leonardo, and all the wireless Northeastern team for inviting me. Let me start sharing my slides and also set up my timer. I think we are good to go. All right. Yep. So hello, everyone. Good morning, good afternoon, good evening, depending on where you are on the world. It's a great pleasure to be here for the Open 5G Forum Fall 2021 edition today. I'll be talking about, well, the title says ORAN, a great playground for AI. Let's play. But the talk is not only ORAN. At the end of my talk, I'm going to touch upon a couple of things that we do related to ORAN, but I will take you through the other works that we do in the area of 5G, 6G, and of course, how we use machine learning algorithms to optimize, to help 5G and ORAN to self-optimize. In my lab, NETCORE, we are primarily focusing on a couple of the fundamental problems in wireless. One very fundamental problem is, of course, resource allocation. That resource allocation could mean a lot of things. Out of them, we particularly work on user cell or user beam association, spectrum allocation, power allocation, and also computational and cache resource allocation. In this slide, I'm showing one of the works that we did as an example in where we focused on two things, two types of resource allocation. Number one is user beam association, and number two is physical resource block allocation once the users are allocated or get attached to their respective beams. So we use, in this work that was published in 2020 in GlobeCon, we use two different types of machine learning algorithms. As you might be familiar with the general categorization of machine learning algorithms, we have supervised learning where we have the labels for the data, unsupervised learning where we try to discover the pattern in the data, reinforcement learning, which is a control type of learning, and then deep learning, if we can put it like a third category that can actually cover the other categories, is originating from the neural networks and trying to find, again, maybe classification or patterns in the data. So for the user clustering, because users are mobile and they are moving at certain time intervals, to determine which beams should cover each group of user, we group the users. And for this, we use a well-known clustering algorithm that's called DV-scan. After the users are grouped under certain beams, and beams are tracking basically those clusters, we use deep reinforcement learning for physical resource block allocation. Physical resource block allocation is a problem that has been studied widely in the wireless literature. There are optimization solutions, algorithmic solutions as well as machine learning solutions. So Q-learning, reinforcement learning, or DRL has been applied in a lot of times, and our works actually are among the ones that use DRL heavily. And over here, the objective is that, or the idea is that 5G and LTE as well, they're using OFDM. And in OFDM, you have subcarriers and time resources. So they're split between the users. And the problem is actually scheduling which user where kind of problem. So with this DB-scan-based user clustering or user clustering and beam association and DRL-based resource allocation, we showed that we can optimize or we can improve the performance for URLLC and EMBB users. And the reason we looked at URLLC and EMBB users is that they're two competing users. As you know, EMBB stands for Enhanced Mobile Broadband. These are throughput-hungry users. They want to get the best and most of the physical resource block allocation. In the meanwhile, URLLC traffic is arriving and it is trying to puncture some resources from the EMBB. So how do you handle these two types of traffic without hampering their performance or giving their best, basically? So URLLC would be interested in, excuse me, URLLC would be interested in having low latency. And in the top figure, we see that under high load regime, the latency that is obtained with our algorithm in comparison with the state-of-the-art algorithm at the time, 2020, we compared it with an algorithm that was proposed in 2019, I believe, by Nokia researchers. And we were able to reduce the latency for URLLC users significantly, and that did not come at the expense of EMBB throughput. As you see on the bottom picture, the throughput of the EMBB users is also improved by using our deep learning approach. Now, after getting some promising results, one starts to think, being a researcher in an area, then what's the trade-off? I mean, there has to be something wrong with this, right? You can't get everything super right in wireless with so much correlated parameters. Of course, I mean, everything is not, cannot be painted in pink. So what happens here is that there is a significant amount of time for training. So all these decisions are happening in the TTI level, 1 millisecond, but then the training takes so much, thousands of TTIs. So the assumption here is that what one can do is we could do offline training, but then the conditions that you do training should not change so much when you're actually taking the decisions, which might not be the case when you apply it in the field. So we kept on innovating in this field, and we came up with the idea of applying a relatively novel technique in machine learning, which is transfer reinforcement learning. Transfer learning has been known for a while. I mean, it's probably quite obvious that that type of learning should be there because, I mean, human learning is, we don't learn everything from scratch, right? we learn something and then we apply the same knowledge to a different area. So if you have two data sets, then it's quite understandable that you can transfer the knowledge from one data set to the other. When we have transfer reinforcement learning, it's a bit different, and this comes from the robotics literature. The analogy is that you can have a robot picking a mug or a pen. So the task of picking something is actually the same, but the objects are different. So there are some things that are transferable, but you have to really know what that is. Like you can't transfer picking an object and walking out of the room. So we gave some thought on this, and we said, I mean, our problem is, okay, we're getting good KPIs, but then the convergence is high. So can we use a technique to reduce the convergence? And then how do we do this task mapping? In this paper that we published in 2021 in IEEE Transactions on Wireless Communications, we started with expert G-node Bs that look like actually LTE base stations, omnidirectional coverage, and they only have the problem of user-cell association. After our expert G-node Bs know this problem in such a network setting, we said, can we have the learner G-node Bs, who would be the actual field-based stations, to learn how to do user-cell association, the same problem, but in a directional cell setting, and also resource block allocation. We show that some improvements can be obtained without hampering the KPI, user-related KPIs like throughput, latency, and packet drops. But still, we have some way to go. Basically, we can shorten the convergence time. However, we still have some problems in scalability. Also, deciding which tasks to transfer actually requires human knowledge. So if we are trying to get automated networks, automated operations, then you have to have something to address this as well. But in any case, we realize that transfer reinforcement learning has a lot of potential. So we used it for RAN slicing as well. But then the previous slide, what I showed as transfer reinforcement learning, assumes that we have one expert. So we were thinking, like, how do humans learn? Like, you go to a college and you learn from multiple professors, you go to multiple classes, and then you combine your knowledge. So why don't we have multiple experts or multiple trainers? And in the RAN slicing problem, we focused on, and maybe I should give a little bit of background on the RAN slicing problem. Network slicing, I mean, it's been a popular topic in wireless for a significant amount of time. But transport and core slicing are the ones that has been addressed. There are still open research areas in RAN slicing, edge slicing. And the fundamental problem is being able to do slicing in the close to real time. And also the resources are much more limited when we come to the RAN side. Nevertheless, in our paper, that is going to be published or accepted to CCNC conference in January, we showed that the convergence, now we see over here both improvement in reward, by the way, and also faster convergence. So that can be significantly improved. So as you can see, there's lots of room for improvements when using machine learning algorithms, but there are also trade-offs that we need to address. And the next work that I want to talk about today is one of the works that we did with our vendor partners. And here we looked at carrier aggregation. You probably know carrier aggregation is a fundamental capacity boosting, throughput boosting technology that we had in LTE Advanced, and we are having it in 5G as well. But the problem here is that how to allocate the primary component carrier and then how to add the secondary component carriers without incurring too much channel monitoring overhead at the UEs. Because that means, like, you are watching a seminar like this or watching a video, your phone is, let's say you're outdoors, your phone is doing carrier aggregation, and to increase the throughput, it starts monitoring the 5 component carriers at the same time. You're going to drain your battery really fast. So we don't want to do that. We want to reduce the number of active component carriers so that we can save some UE energy, but we don't want to compromise, or we don't want to lose from throughput and latency performance metrics. And we show that if we have a dynamic traffic pattern and we use machine learning, particularly deep Q learning, it is possible to get performance close to activating all CCs in terms of throughput and latency, but in the meantime, using less component carriers on average. So sometimes you use more, sometimes you use less, but on average, less CCs are monitored.
Thank you,
so
Melike. Time's up. So if you could go toward the end of the presentation.
My timer is also up. So yeah, let me just summarize a couple of ideas and get back to the questions Q&A side. So we have some works on ORAN that address energy efficiency of ORAN using machine learning. And here we use, for example, tabular Q learning, and we used actor critic learning for CUDU selection in ORAN. But overall, I mean, the idea is our group and lots of other groups are working in the area. It's an exciting area, number one thing. And why it has become so exciting is that, softwareization, cloudification trend are faster innovations, and we are running towards, I would say, more agile and automated networks. So that's what is really interesting for us. So this is my group of students, and I would like to thank everyone for listening to my presentation.
Thank you very much. I have a question on this and very interesting topic. And how do you think ORAN can help in these kind of problems and challenges that you're facing?
Well, I'd like to think like, how can AI help ORAN to address the challenges? I think ORAN is increasing complexities, but it's increasing complexities for the good. I mean, there is going to be open interfaces, there's going to be lots of innovations, and lots of new maybe vendors innovating on, I'm not sure if it is any more correct to call them vendors, but lots of companies trying to innovate in a softwareized and cloudified infrastructure. So ORAN can help maybe in making a challenging environment and also an open environment that is open to competition, so that can help AI. But I think it's the AI that should help solve the complexities in ORAN as well. So maybe it's like they're like the sides of a coin.
All right, thank you very much. There is another question, if you could just address it shortly. Could you give us an idea about the size of DRL agents applied to 5G? For example, number of parameters, like millions of parameters, billions of parameters, or actions?
Yeah, that's a very good question. And actually that is an impacting factor, like how fast you can converge. In terms of number of actions and states in our MDP models, we try to keep it simple, because obviously if you have, how much more you have action states, then that much more you have complexity and longer convergence time. And most of the times we're looking at a couple of base stations as agents, so it's not millions and billions for sure. If it was the UE side, yes, it would have been more reasonable to look at more, more number of agents, but still scalability of these algorithms is also needs to be studied. So convergence and scalability are the factors impacting the, what is asked in this question. And in our approaches, we try to keep them as simple because we know otherwise we're going to be in trouble.
All right, thank you so much for being here today.
Thank you very much.
And we're gonna proceed to the next speaker. Our next speaker is Matti Hiltunen, and Matti works at AT&T, and he's also involved with the ORAN software community efforts. And he will give us a perspective on the ORAN software community and open source RIC platform.
Thank you for the introduction. I'm assuming you can hear me okay.
Yes, I can hear you.
Okay. So let me share a slide deck. So I'm reusing this slide deck that Thoralf, who is the PTL of the RIC project, and I used in the Open Network and Ed Summit. We were talking about the near real-time RIC and the RIC apps. You can find the full presentation on the ONES website if you want to see what Thoralf said and what I said in the full presentation. So this is somewhat shortened to fit the 10-minute time window. So I have been the PTL of the RIC app project from the beginning. I handed over that task to a person from HCL a few months ago, but I've been involved in the OSC community from the beginning. And in the RIC app project, the purpose is to build open source XApps for the OSC RIC platform. We started at the same time as the RIC project, and we started from the very beginning to implement XApps. So this was before any of the specifications were approved, any of the APIs were standardized, and even while the platform was very much still evolving. So it has been kind of an interesting process, since we're kind of building XApps on a platform and standards that keep on changing. But I believe it has been a very useful exercise, because we have learned a lot by building XApps and kind of finding out what the pain points are and what commonality there is in the XApps. and that those common things we can move into the RIC platform as a part of SDK library. So it has been a useful process. And also in this process of building XApps that use different E2 service models, we have enforced that the platform stays service model agnostic, so that any XApp using any E2SM can run on the RIC platform. We ran into that problem early on where some of the service model specific features had creeped into the platform kind of unexpectedly. And then when we were trying to run off some of the open source XApps, we realized that something would break. So for the XApps, we have a set of what I would call demo XApps. We call them Hello World, that show how to use different RIC features from different programming languages, C++, Go, and Python. But in addition, we have started building from the very beginning more elaborate use cases. A traffic steering use case has been something that we've been building towards from the very beginning. We added anomaly detection to drive this use case recently. And we're starting to explore things like, well, what if we have geolocation of the users? Could that, for example, improve traffic steering or anomaly detection? And things like network slicing and the new E2SM RAN control service model that is formally getting approved this month. And while the XApps in the community are relatively simple, I believe some of these ideas could evolve into commercial versions eventually. So we have been building this community throughout the years and throughout the releases. Initially, we only had two companies, AT&T and Samsung, contributing XApps in the initial release. But over the years, we have added HCL, and HCL is now taken over the PTL role. They have contributed anomaly detection, throughput prediction, and benchmarking XApps. Samsung started by providing a KPI mon that implements metric collection using the E2SM KPM. But in the previous release or the D release, they also released demo XApps for Go and Python. AT&T is still maintaining XApp for metrics calculation and the C++ Hello World XApp. China Mobile added a machine learning XApp in the D release for load prediction, and a university in Brazil has taken over the maintenance of the traffic steering XApp that was originally developed by AT&T. And in the E release, Mavenir joined the group, and they are contributing a XApp that implements the E2SM RC or subset of it. So we have gone from 2 contributing organizations to 6 organizations that are contributing code to the XApps. In addition, Viavi has been working closely with us to provide a simulator that supports the use cases. And finally, in the OSC community, the RIC SDK repos are under the RICApp project, and Facebook and VMware have agreed to contribute code into these repos, hopefully by the end of the current release, but if not, then in the next release. So I collected some statements from the community, but I think the most relevant for this presentation is the statement from the professor in Brazil. He finds this to be a great opportunity for academics to work on real-world problems and collaborate with the leading businesses in 5G technology. So if you're participating in the RICAP project, you'll be on the phone calls with Nokia, Samsung, Mavenir, etc. So it's an opportunity that students usually do not have. So I would definitely recommend, if you're interested in working in the OSC community, please reach out to me or the new PTL or the community in general. So to give you a little bit information of what we are trying to accomplish in the use cases, in the D release, we were hoping to achieve the control loop where we collect metrics from the RAN using KPI-mon and the KPM service model, store them in the influx time series database, and use anomaly detection to trigger handover decisions and QP throughput prediction for kind of picking the best new cell for a UE that is having a performance anomaly. Unfortunately, we are not able to integrate the KPI-mon and the simulator in the D release, so we are still hoping to integrate that in the E release, which we are working on right now. That will be released at the end of this year, and the code freeze is coming up in a couple of weeks. So in the E release, we are adding this load prediction XApp from China Mobile. It's using machine learning, and the RAN control XApp from Mavenir. And we are starting to look into, for example, network slicing, which is a high priority use case in ORAN. And the first step will be kind of understanding the slicing in the anomaly detection and being able to detect anomalies per slice. And I think people in this community and on this call are probably interested in machine learning. So we have actually about half of the open source XApps are using machine learning in one way or another. The anomaly detection is an example. It detects performance anomalies for UEs using a trained machine learning model. The specific techniques used is isolation forest, but the other XApps use different techniques. And while we now build and train the model offline, in the future when the other OSC components mature, we can definitely look into training the model in SMO, a non-real-time RIC, and updating the model dynamically. And finally, I'll talk about a little bit about the bouncer XApp. It's a little different. It's not a use case. It's really an XApp to test the performance of the RIC platform. Performance is, of course, critical for near real-time RIC. We want to be able to control the RAN with, say, around 10 millisecond control loop latency. Of course, we want this near real-time RIC to be able to handle a large number of E2 nodes and large number of messages. So in order to be able to test if the RIC platform can support that, we need to have a kind of a testing harness. And the testing harness in this case consists of a bouncer XApp and an E2 simulator. And the bouncer XApp will, well, the E2 simulators will first connect to the RIC instance, and then the bouncer XApp will issue subscriptions to these E2 simulators, and then it uses this Hello World service model that allows us to do insert control loops where when a E2 simulator sends a report to the bouncer XApp, it will send a control, and the E2 simulator will measure the difference between the report and control messages. So this is very powerful testing platform, and I believe that this will be very useful for not only the OSC RIC, but other RIC implementations as well. I think I kept my presentation to that 10 minutes, so that was my last slide.
Wonderful. Thank you so much for your presentation. Very interesting topic. And there's a question in the chat, and the question is, did you profile the performance of the ORAN software community RIC with the bouncer XApp that you just showed right now?
Yes, we have been doing that, and I wouldn't say that it's completed. We are encountering some issues, especially when we start connecting larger number of E2 nodes. But and hopefully we can actually iron out some of these issues before the e-release, so we can show some good results in the e-release. But it's still work in progress. especially when we started connecting like hundreds of E2 nodes into one RIC instance.
All right. Thank you. And another question is, if you could elaborate a little bit on how people can interact with the ORAN software community and contribute to it.
Well, I would suggest that you maybe reach out to me or reach out to the new PTL, Sunil Singh from HCL. We have regular meetings that are public meetings. They happen every other Tuesday morning, New Jersey time at 9 o'clock. You can find the meeting bridge and meeting invitation on the OSC web pages. Those meetings may be a little hard introduction because they're kind of working meetings and we're going through the current blockers and current bugs. So it might be good to kind of have an initial discussion to kind of share ideas of what you would be interested in doing. We can definitely, there's opportunity to basically contribute to the ongoing work. For example, we've been looking for somebody who would be interested in maintaining the Hello World C++ XApp. But then there's definitely, if you have any ideas that you want to pursue, like new XApp ideas, it would be good to discuss first and kind of find how they would fit in and what hurdles there would be. We are very open, even though there are kind of OSC use cases that are kind of driving the main line of the work. I don't think we would say no to any new XApp ideas. We just have to, the challenge will be partially to find out how we can kind of test that XApp. We have had some issues kind of having a good simulator, and I think Northeastern hopefully will help us that in the OSC community. Yeah, reach out to me or reach out to the new PTL, check out the OSC wiki pages. And yes, I'm really welcoming to new contributors. And if you just want to listen on the meetings to see what's going on, there's nothing wrong with that either. So everybody is welcome.
All right. Thank you so much for being here.
Thank you.
And we're now gonna move to the next speaker, Rittwik Jana. And Rittwik is the chief architect of RAN intelligence at VMware, and he will present us the VMware work and products for Open 5G networks.
Okay. Great. Thank you. Can you hear me? Yes.
Yep.
Okay. I'm going to maybe just give a quick overview of OSC. So it's good adjunct to Matti. So OSC is the ORAN software community, and part of that is we're in our e-release, right?
Sorry, Rittwik, if you could enter in presentation mode, that would be great.
Okay. Yeah, I don't know if that's going to work. Does that work?
Yep, wonderful. Thank you so much.
Okay, yeah. Yeah, so I'm the requirements co-chair along with David Kinsey. We have this meeting where we discuss about all the different use cases and the requirements as part of the open source community. You can come to those meetings and you can propose new use cases. We also discuss about what kind of lab preparation that's going on right now. How do you get engaged in OSC? So that's something that we will definitely love to get our communities together. And then this is a very high level overview. I don't want to take too much time, but you can get to the ORAN wiki via this URL. All the information is over there in public, wiki.oransc.org. And our job is really to implement the ORAN standards that come out from the ORAN Alliance working groups. So the ORAN Alliance working groups are creating specifications, right, from all these different working groups. And then we ingest those specifications and we try and implement those in all these different projects that are in OSC. So as Matti was talking about the RIC app project, application project, which deals with XApps, there are other projects where we deal with open source ODU, for example, or the open source RIC. So yeah, and now what we're trying to do is we're trying to stand up an end-to-end lab that will exercise some of those use cases, that you can attach an actual UE, which will talk to an XApp, and that XApp may have some machine learning in it. So that's essentially the cycle. And then we, of course, use a lot of information from ONAP, and we contribute upstream also to ONAP and these other organizations. Right? OSC is built out of this technical operating committee. So there are a couple of important meetings, if you like. The TOC, essentially all of OSC meets every Wednesday morning, about 8 Eastern. 8 Eastern, there's a meeting where all the OSC representation is there, and we discuss various things, from copyright to actual working code and things like that. So, and then there is a Rsac meeting. This is the meeting I was talking to you about. Myself and David Kinsey are essentially running these meetings, where we discuss about the projects and what's going to come in the next release and what's happening in the new release and the current release. Are there any bottlenecks? How do we track these projects? And then there are individual projects, if you like, where if you're interested in a particular aspect of the project, let's say you want to build a simulator. So you can get in touch with the simulation PTL and you can add features into the simulator, or the XApp, you can talk to Matti, or the the new PTL. Right, so that's really how we kind of operate. This is a little bit old, the OSC status. It gives you a very high-level overview of how many million lines of code there is. I think this is D release. By E release, this will all get updated. So there's a lot of contributions that are going on. A lot of people are contributing code, and they're actually trying out these different use cases that we're talking about. With respect to machine learning workflow, here's a very high-level overview of how machine learning is happening. You will have essentially ML designer that will conceive the particular problem. Once that particular problem is conceived, it will basically upload, the model will get trained over here. And that model training happens through data that comes from the RIC into a data broker. Then once that model is trained, it gets into the ML catalog. The ML catalog can be part of the SMO or could be outside the SMO. So the SMO is the service management and orchestration shown in this dashed box, if you like. And then it gets uploaded into the ML catalog inside the non-RT RIC. The non-RT RIC can then deploy the model either inside the non-RT RIC engine, or it can deploy it inside the near-RT RIC engine. The ML models get deployed through O1 protocols, and then you activate the model. And when the model is activated, basically inference is happening or predictions are happening. And as part of that, there are some feedback that can go back up to the non-RT RIC, or you can actually send back to the training host where the model gets retrained. So essentially, it is one example of a life cycle of how models get designed, trained, and deployed, and then finally retrained and redeployed, right? So in these end-to-end control loop use cases that Matti was showing, right, we are using some aspects of machine learning. Although I don't know whether we actually use the entire life cycle management as in the previous slide, but we are doing bits and pieces of machine learning today. Okay, the other aspects I wanted to discuss is, okay, maybe if you look at how the OSC testing framework is set up, we have a lab in New Jersey and another lab in Taiwan that is getting erected right now. So that lab in New Jersey has these following blocks. We have a ORU server. We have an emulator, which will do the RU emulation. We have a DU, open source DU, which consists of DU low and DU high, so L1 and L2. And then we have the near RT RIC clusters with all these different functions, subscription management, E2 management, A1 management, right? All these functions are there. And then we have the SMO cluster, which basically has the service management and orchestration routines, right? So how do you start an RAP? How do you build a non-RT RIC engine inside it? So there's a slide later on that tells you what exactly is in this. So this is essentially a lab that is open to anybody. And if you want access to the lab, just get in touch with us and we can give you access to that lab. Bear in mind that during the E release or the F release, work is always going on in here. Different peoples are building different features, and we are doing integration testing or pairwise testing, right? So yeah, let's see. In D release, I think there's a lot of details. I don't want to go through a whole lot of details, but I just wanted to give you an idea of where we are with the SMO. It's a very new project. And the SMO today basically gets measurements from these different entities, the DU, for example. In the E release, there is a network slicing use case. And in that use case, we are basically saying there's a dedicated slice and a default slice. And we are monitoring the performance of that slice. And that monitoring is happening through these measurements that come up to the SMO. And the SMO has an RAP, slice monitor, slice assurance RAP, that looks into each of these slices and sees when a particular threshold is hit. When, let's say, a PRB utilization has been degraded, then what that RAP does is basically sends a signal down to the appropriate DU via O1 to say, okay, you need to increase the number of resources. So that's a closed loop control that we are exercising in OSC today. And for that, you can see that you need all of these entities to be up and running. So a part of the challenge in OSC is really to, since these are all open source items, right? They're not products, they're not commercial products. The challenge is really to have enough functionality in these open source items so that you can stitch all these pieces together and still get a working solution. And so that's where we are currently with all these different projects. In non-RT-RIC project, you will see that there are stub code which simulates the near RT-RIC, and also you can basically administer or create new policies via these A1 policy management service. And so once you create these new policies, you want to test whether that policy is working or not. And you can test it against this framework. The non-RT-RIC has some framework that allows you to inject new policies and test it against a near RT-RIC engine. So again, this is something that is available today. There's also an A1 simulator out there. Okay, I think what I wanted to show is also, let me just get out of this. I wanted to show this aspect of machine learning. I hope you can still see this. So there is a technical report that is published by Working Group 2. And in there, you can see how we're thinking of where machine learning will exist. It can have training over here, and it can have the model host inference over here, and vice versa. So there are different ways as to, depending on the algorithm that you choose, there are different deployment models, if you like, right? So it could either be all in non-RT-RIC, or it could be in near RT-RIC, or it could be non and near both, right? There's also a life cycle, general life cycle that I described before. You have data collection, then there is an ETL process, data preparation. And then once that data is prepared, it is used for training. The trained model then gets deployed, and then inference is happening. And then based on that inference, continuous feedback is always coming up over here, right? And so then the model gets retrained and redeployed. So there's a tight loop over there. There are some use cases. There are some different scenarios. I urge you to look into this and see where each of these model management and training is happening. There are different scenarios for which you'd like to take advantage of. Yeah, I think that is essentially it. If you want to look at a specific deployment, let's say something like this. Basically, the SMO will have data collection, and then from data collection, you'll have the data preparation, ML training, model management, and then model inference. All of this is happening inside the non-RT-RIC box. And this is one particular scenario, scenario 1.1. Scenario 1.2 will have some of these functionalities split into different boxes. So over here, you see ML training is happening in non-RT-RIC, but ML inference is happening in near RT-RIC. And so there is a an approach that you need to take as to where training is happening, where inference is happening, and how data is actually getting fed back through the O1 link. Yeah, so okay, I think that essentially covers what I have to say. Hopefully that gave you a sort of an overview of where ORAN Alliance is with regards to machine learning and what OSC is doing with machine learning also. Yeah.
Right. Thank you so much, Rittwik, for the presentation. And I have a question of my own. So if you could maybe elaborate a bit more on the relation between ONAP, ORAN, and the general SMO.
Yeah. So it's an interesting topic. Let me see. Actually, I was just presenting to somebody about this. Give me 1 second. Yeah. So it's let me share my screen. Yeah. So if you look at this diagram. Here's a picture of what the SMO components are constituted by. You know, there are different components of onboarding and integration, service delivery, orchestration, inventory, service assurance. All of these are part of the SMO hierarchy. SMO stands for Service Management and Orchestration. So here you have an application marketplace that helps developers build applications. And then it publishes into the catalog, just like the ML catalog. Then it gets deployed. And once it's deployed, you have to orchestrate where to place this RApp, right? And then once you place the RApp engine is running, and then basically service assurance kicks in, right? So as part of all of this, implementing some of these components definitely needs ORAN, OSC, and also ONAP. So ONAP has, in terms of service assurance, for example, it has a policy engine, right? So if a system is at fault, the service assurance control loop kicks in. Which network element is at fault? What are the policies that are associated with it? So analytics happens in non-arterial. Once the result of the analytics has happened, that root cause analysis then gets into the service assurance module. And the service assurance module then takes the results of those analytics and ejects a policy saying what I have to do to mitigate that fault. And so these parts are essentially ONAP driven. ONAP has done a lot of work in that. And a lot of the new parts that are coming in as part of SMO is ORAN, right? The RApps, the RIC engines, these are all ORAN. And then finally, EMSs are always there in a RAN environment. You have element management system. So to mitigate that fault, you might have to actually send a control action down to an EMS, right? Either through legacy interface or through some kind of an adapter, right? Where you can talk to multi vendors. That's where I think all of these kind of hangs together. It's a complex system, but as part of OSC, we are only doing some portions of it, not the entire system. Okay, hopefully that helped a little bit. Yeah.
All right, thank you so much. And another question, if you could maybe elaborate a bit on the complexity of testing of all these features and solutions.
Yeah, the complexity of testing in OSC is actually quite high. Principally because it's like I said, it's not commercial products. When you have commercial products, everything has been pairwise tested, all the bugs have been removed, right? So it's a very mature kind of a system. When you deal with open source, the complexity of the testing really comes into, is the feature available, right? So to test these new features in open source has many interdependencies. And so I think we're finding it the hard way that just to do network slicing, a very simple network slicing use case, in one release is quite difficult. It's not as simple as putting things together. You have to get the actual schema, which helps to send instructions to the SMO, right? What is the data that is actually sent to the SMO? And so these things, everything has to be designed step by step. And also because different parties look at it from different viewpoints, in a lot of the OSC calls, we discuss about designing the application in a simple way so that we can demonstrate the capabilities of O-RAN Alliance. That will be very different when you work on a product, because in a product, you have to deal with lots of different edge cases, right? Boundary cases. But the principles of network slicing still needs to be delivered through O1, through A1 and E2. And so that's what we kind of focus. And our job, I think, in OSC is really to make sure that the specifications that come out in O-RAN Alliance is accurate. And if there are gaps, we identify those gaps and send a message back to O-RAN Alliance to go fix the specification. And that is really what I think we're interested in doing. Yeah.
All right, thank you so much for being here with us today.
Thank you.
And I will now move to the next speaker, Vijay Shah. Vijay is an assistant professor in the cybersecurity engineering department at George Mason University. And he will present us the activities of the NSF-funded Open AI Cellular project.
Yeah, thank you, Leonardo, for the introduction. Do you see my full slide or the presenter slide?
I see your full slides.
Great, and thank you, Michele, for the invitation. It has been really great listening to all these great speakers. And Rittwik, thank you for that great introduction, because that is what this project is based on. So as you can see, it's called Open AI Cellular, where obviously open stands for open source. And I do have some other appointments with CCI and Virginia Tech, where CCI is actually a Commonwealth of Virginia initiative, a pretty big initiative, about $100 million over 5 years to move the field of cybersecurity, NextG, and autonomous systems. So the other co-PIs, as you could see, Vuk, who is also a co-PI on the air power, he leads the MSU team, the Mississippi State. And I was leading the Virginia Tech team while I was still at Virginia Tech. And now, given that I'm at Mason, the things have changed a bit. But anyway. Okay, I was planning to give a little background on O-RAN, and then I heard all these nice presentations. I said, no, that is not really needed. So let me go directly into the project. So, I mean, there is no denying here, right, that AI is well suited for wireless communication for many different reasons. And I have listed some of them, that it can learn and estimate these near optimal settings, especially in 5G kind of settings where you have so many different parameters to tune. Then also you can generalize a solution which can respond to new situation. And if you go after this model-driven approaches, obviously that is not something you can do, and so on. So now there is a general understanding in the community that if we do the AI right, it probably could be the basis for realizing 6G. But it's not that simple. I mean, obviously we have a lot of optimism on AI, but the reality is that there still is a lack of sufficient real world experience at a scale. And obviously Colosseum is contributing to that, but I think it's just the beginning. And the second thing is that AI in the network has to be extensively tested, right? It's a production network. There are billions of users using it. So you cannot simply deploy AI because it works on certain setting unless you have really tested it. So that's what motivates our work. So before we go there, let us look at some of the key research questions. Is that, how do we design cellular networks to be more AI suitable? I mean, if we had explainable AI, right, then obviously we could know, let's say, this different comprehensive testing and performance, which is literally not existent as of now. So this problem has to be addressed with answering some of these questions, and that's what actually motivates our community research infrastructure, where we want to spur the experimental research and development on AI-enabled cellular radio access network controllers while leveraging the existing larger scale community research test beds. So what is OAIC? So it consists of two major things. The first one is the AI-enabled controllers, the AI RAN controllers. And the second one will be the AI-enabled RAN testing framework. So the OAICC, which is the controller, it will leverage the existing open source cellular software, like SRS-RAN is our choice as of now. And we are going to extensively use ORAN for this. And then it will be based on SDRs. As I said, it will use community SDR testbed like Virginia Tech Cornet, which is a mid-scale community research testbed with about 48 software-defined radios. We are adding some and USRP antennas, and then there is CCI, which is deploying another 70 USRPs on the ceiling. So that could be another platform where you could test. And obviously, finally, the air power. So here, our focus is mostly on the PHY and MAC. The reason is, which I'm going to talk in the next slide, but the idea is that we want to focus on near real-time break because it does have some capability of implementing some MAC functionalities. And the second one, we would like to explore that can we deploy the sub-millisecond real-time break, either in the DU, RU, or maybe in the CU. That's not that simple. If it was that, probably it would have been deployed by the implemented by now. So we would like to explore what exactly is needed. And these are some of the research and development questions we ask. That can we support this new data type collection so that we could do some physical and MAC research? Can we support some dynamic functional split so that we can have this IQ data in frequency and time domain so that we have to go beyond 7.2x? And obviously, because we want to do AI, we want to support AI ML model in those lower layers. And finally, we'll have to support some additional interfaces. For example, in our case, we want to have this AI testing framework. So there doesn't exist as interfaces as of now. So we like to develop that and make it available to the community. There may be more, which we still do not know, given that it's just started. So this is the reason why we chose MAC and PHY, is because we ran this community survey, and I'm sure a lot of people on this call did participate. So thank you very much for that. And we saw that about 80% believe that ORAN is the way to go. And actually only 1% says that no, so it's literally 99% in a way. And then 65% are interested in other functional split, as you could see. And PHY and MAC, if you see in the figure 3 and figure 5, they both indicate that PHY and MAC are of highest interest to the community. So we do have some initial development of OAICC. As of now, it supports this ORAN-enabled 4G LT system. SRS-RAN NSA just released a couple of weeks ago. So we were able to test that with the 0MQ simulations, but not really with the hardware yet. So that's where we are working on. We are facing some issues with the USRP X310s, but hopefully we'll figure that out very soon. And as I said, our focus is more on the near real-time break and sub-millisecond real-time break. So that's where we are focusing on right now, rather than exploring non-real-time break too much. CCI does it, so that's complementary to us, given that we work together very, very closely. And some of the AI RAN controller accept that we have developed and implemented and reproduce what has been there are the following. So the first 3-4 are directly coming from the OSC. The other one is the RAN slicer XApp is the powder one from University of Utah. And then currently we are developing several scheduler XApp that includes the proximal, not proximal, I'm thinking about the other paper, okay, for proportional fairness and age of information scheduler and so on, and they will be available again to the research community latest by next April. Okay, so now the OAICD framework. So here the idea is that we want to build this automated multitasking and distributed testing. And the reason again is that AI models are enabled for 6G research, but the inability of current theory to explain or prevent failures in the AI model does emphasize the necessity of having such a framework and appropriate environment for testing AI models deployed as cellular RAN controllers. We want to use both the modes, simulation and STR hardware. And the reason we leverage AI for testing as well is because it's just a very large test space. So we want to do AI for AI. So why do you care, right? So you should care because it's a fully open source developed for the for the research community, and given that you belong to that category, it makes sense that you'll be able to leverage some of these, not some, actually all of these code, because you'll make them public and available either via GitHub or our website. So similarly, you can use the OAI-CC platform to build your own AI controllers for the physical and molecular research. You can use our OAI-CT to test your functionalities. Source code will be available, so you can literally add new functionalities to the OAI-CT if needed. All the data set will be made public. You can also use the platform to collect your own data set. And finally, there will be proper documentation and all the services tools, and also the OAIC design document that will be made available very soon will be available to you. So given that, hopefully I have done enough to attract your attention, this is the roadmap. So our code release is scheduled for Q4 of 2022, followed, and then after that, every 2 quarters, there will be a new release. For the OAI-CT, the same format, but the first one will come in the Q1 of 2020. That's the anticipated roadmap that we have now. But the good thing is we are doing really well on time, and we are set to meet our first release very, very soon, hopefully by April 2022. And similarly, the tools will be released along with the OAI-CC code. And finally, there will be 2 workshops. So you all are invited. We'll definitely make those available either through our website and hopefully through other outlets, so that many people can attend and get involved with OAIC. And finally, we definitely would like to hear your research interest, discuss collaboration opportunity, and define R&D that are of interest to you, and hopefully write some joint proposals so that we can keep going beyond the 3-year support from CCRI. We do seek industry involvement with building our OAIC community infrastructure. And Rittwik obviously was, thank you so much. He was one of the few person who supported us with the collaboration letter when this proposal was submitted. And finally, please reach out to us, me, myself, or some other OAIC PIs and co-PIs if you are interested. Thank you.
All right, thank you so much for the presentation, Vijay. And we have a question in the chat. What kind of access are you going to provide to the general community?
So all the software source code will be available. Like I said, via GitHub, that's what we are exploring right now. And we'll also give remote access, like the one you did do for Colosseum, and the one we do the same for our coordinate. That you'll be able to log in and do real experiment with our platform.
Right, thank you so much. And maybe another question: how easy is it for other researchers to use OAIC and integrate custom logic into it, or to use it to test functionalities?
That's a very good question. So that's literally what we are working on. Again, we are building this design document, and we would like to make it as simple as possible. Like I said, the source code is going to be available to us, available to you. So I hope it won't be that difficult, but we'll be there to help you if you have any additional questions. So we'll have working groups and all, and documents and tools, services, everything will be made available to you.
Right. Thank you so much for the presentation. And we will move to the last speaker of this session of short talks. The last speaker is David Johnson. David is a research associate and software engineer in the Flux Research Group in the School of Computing at the University of Utah. And he will describe how the Powder platform is contributed to software for O-RAN networks.
Hi there. Thanks a lot, Leonardo. Yeah, the focus of this talk is kind of 2 things. It's the Powder platform, which is one of the Power testbeds sponsored by the Power Project Office and National Science Foundation, and then a brief tour of how we try to enable O-RAN experimentation on that platform and some of the stuff that we've done with that.
Yeah, so if you could enter in presentation mode so you can see the slides full screen.
Unfortunately, I can't. When I tried to do that earlier, it locked up Chrome and X almost. So I don't dare to do it for fear of losing my desktop. So hopefully we can make the best of it. Thank you.
Okay, thank you.
So our overall goal here is to get real ORAN software working in the most end-to-end sense that we can, all the way from the software-defined radios and hopefully eventually ORAN devices like ORUs, all the way up to the SMO layer. So just a little bit of background about the Powder test bed. University of Utah has been building test beds for many years. Powder is a specifically wireless, mobile wireless focused test bed. So we have many kinds of devices, hundreds of compute servers, SDRs deployed around the University of Utah campus, both in sort of what you can think of as base station form factor and UE emulation form factors on tops of buildings and sides of buildings and on campus shuttles to give a flavor of regular mobility. We have a sophisticated way of describing experiments and packaging experiments that we hope facilitates reuse and acts as building blocks for describing and creating experiments on the platform. And I'll talk about what this means in the ORAN context in a little while. Thinking a little bit about the experiment process on Powder, the idea is that you first describe the kinds of experiments that you want to run using our profile mechanism. So you describe the hardware and software that you want, the software configuration. You might package some scripts to automate extra configuration that the platform doesn't do for you. And then our control framework, which is sort of like cloud orchestration, will deploy that on bare metal, VMs, containers, and configure radios and configure wired networks as well to realize the experiment that you want. In this talk, we're kind of focusing more on the software building blocks rather than the SDRs. We do have, as I said, a number of different kinds of radio devices, but I want to focus a little bit on the software here. So like I said, the profile mechanism is you can think of it as a recipe. And we've created profiles for many complicated software stacks. Kubernetes, OpenStack are two of the cloud stacks we focused on, and then going beyond that to ONAP and ORAN. The idea is that with a point-and-click GUI and a web interface, you can just instantiate these profiles and bind them to real hardware that's remotely accessible in our test bed. Many of our profiles contain a number of parameters, so you can customize your deployment according to those parameters. Moreover, the profile mechanism is designed so that you can fork it in a Git sense. These profiles are often packaged as Git repositories containing both a program that generates a description of your experiment from Python source code. So you can literally fork them and extend them as needed if you want to customize your deployment. And we have an API for automating these experiments as well with custom parameters. So let's look quickly at what our web interface would look like if you were trying to instantiate our ORAN profile. So there's a little wizard that you can click through. And assuming I had clicked through the wizard, you would see that there's a number of parameters you can change. You might want a multi-node ORAN parameter or ORAN experiment. You might want to customize the resources that are there. You might choose to install different RICs or different versions of those RICs. You might wire this experiment to other experiments using private isolated VLANs. And these other experiments, for instance, might contain wireless resources. So this is a long-running ORAN experiment that I just took a quick snapshot of in our dashboard. That is just a single node. It's got kind of a dangling pointer off to the other side, and that's connected to a shared VLAN. And I've used this experiment many times to run ORAN demos. So I'll connect it to different kinds of Powder wireless resources, whether it's our emulator or our indoor over-the-air test bed or outdoor resources. Now I want to pivot a little bit to some of the ORAN work that we've done on Powder. So we've made a lot of use of the existing open source community pieces, especially from the ORAN software community. So thanks to the work of Matti and Rittwik and their development teams creating this so that we could build off of it quickly. And the software radio systems folks who build the SRS RAN software. So our approach here was, and the goal again was to build this end-to-end software stack in the Powder context. So what we did was maybe not a super novel RAN slicing implementation, but the approach was pretty simple. Slices will share the same spectrum. There's a northbound interface to create slices and create UEs, adjust resource allocations in terms of resource blocks dynamically. So that's represented up in the, this is the classic figure from the ORAN software community's webpage showing the RIC and RAN nodes going down further. So the Roman numeral 3 annotation there in the RIC shows where our custom XApp sits, and this implements a custom service model that we wrote that exposes our RAN slicing to a northbound RESTful API. In the next box down, you can see Roman numeral 2 kind of on top of the E2 interface. That's where we implemented the E2AP protocol in the SRS RAN software, as well as our custom service model. And numeral 1 there is the SRS RAN eNode B software, which contains our E2AP agent. And I should say we're working on porting that, of course, forward as SRS RAN pulls forward into 5G. This is another view of that same kind of architecture picture that shows more specifically the pieces of the ORAN RIC that we used, how our XApp plugs into the RIC. There's a RAN slicing manager at the top that operates over a RESTful API. Eventually, we hope to push this into a more full end-to-end realization that uses SMO pieces such as ONAP and the O1 and A1 interfaces, just so that we have a very complete use case. And then going southbound from the RIC, you can see our E2 agent inside of SRS RAN and the service model contents flowing over that. Our E2 agent also exposes the KPM service model, and this allows us, has allowed us to build some closed loop automatic slicing based on policy into our XApp. I've included this sort of omnibus slide with a number of pointers to where you can get more information and pointers to using this stuff inside of Powder. Again, our goal was to automate as much of it as possible, so you can go ahead and use this today and use it in Powder if you go to powderwireless.net and get an account. And our ORAN profile does include both the OSC RIC, the Cherry and Dawn releases, and the emerging ONF SD-RAN RIC. The public release, that is. It's still in the incubation phase in the Open Networking Foundation. So with that, thanks. And again, thanks to the OSC folks, especially those who are on the call, and the SRS RAN team for all the great software that we were able to take and extend. So this was obviously a very brief presentation, but these slides I think will be posted online if you want to reference them further. And with that, I'm happy to take some questions.
Thank you so much, David.
Sure.
I have a question of my own.
Sure.
If you could elaborate a little bit more for our audience about the scale of compute servers and radio nodes in the Powder platform.
Yeah, let me go back to this slide, this first slide here. So we have a pretty diverse selection of compute nodes. I would say that it's somewhere, I don't know, 1,000 to 2,000 servers. Some are ARM, most are x86. They tend to be split differently. Their configurations are different depending on whether you're emphasizing compute or memory or disk. So there's a lot of variety there. They all have very high-speed interfaces. Again, a lot of diversity there to enable different kinds of research. Powder is federated with the Cloud Lab testbed, so it has access to some of the Cloud Lab resources as well. As far as radio resources, I'd say that we have 10 to 15 rooftop-style base stations, each containing some SDRs. We're in the process of deploying some massive MIMO base station via our collaboration with the Renew project from Rice University. And these are 64-way massive MIMO stations. And again, those will be deployed on rooftops around our campus, and we're in that process now. We're deploying more and more software-defined radios on the University of Utah campus, including a densified deployment where the radios will be embedded in just a more dense configuration that is nearby, that is adjacent to all of the mobile shuttle couriers that also have software-defined radios. And I think the specifics of how many and how many SDRs per station are available on our website.
All right, thank you so much.
Sure.
And if there are no other questions, I will hand the floor to Michele, and thank you again to David and to all of our speakers for this talk session.